This is lecture number 49 of this course. We begin this lecture as usual with inner product space V over R or C. Recall that on such a inner product space a linear map is said to be self adjoint if one has the following. So, if A star equal to A, that is, in other words, for every x y in V, inner product of A x y is same as y. Then for an we say A is normal, if A commutes with its adjoint. Okay. So, self adjoint maps are normal. In the last lecture we proved the spectral theorem for normal operators. What does that say? It says that if A is normal, then A has an orthogonal eigenbasis. A has an orthonormal eigenbasis. Okay. So, again I would like to remind you that this self adjoint, this term is more or less a general term. If the vector space is over R, then we call self adjoint maps as symmetric maps, and if the vector space is over C, then we call self adjoint maps in that context are the Hermitian maps. Okay. And the connection and if you look at choose an orthonormal basis of V and look at the matrix of a self adjoint map, then we will get symmetric matrix or Hermitian matrix accordingly as the vector space is over R or C. Okay. So, yeah. Now, we will talk about more general maps, namely and we will talk about unitary operators. So, before that we need the following. So, just let us prove it as a lemma. So, though this lemma is not required to define unitary operators, however, the properties which will be equivalent to the definition of an unitary unitary map. So, there we may need this, therefore, it is better to prove that in the beginning to begin with. So, as usual A is self adjoint, suppose A is self adjoint, we assume A is self adjoint. And for every x in V, inner product of A x with x is 0. If so happens, if for a self adjoint map we have this, then the map is itself 0. So, that is not quite difficult to see. So, for a proof what we just do is so you take any x and y in V. So, since this is there, so what do you want to prove? We would like to prove x, we would like to prove. So, right, for if we can prove that for every x y x y is 0, then we will be done. But how do I get these terms from having knowledge of the knowledge about the values of these terms? I repeat, how do I get these terms having the knowledge of the value of those terms? So, the natural way is we have to look at the following: A of x plus y when we. So, what is this? A x plus a y, inner product A x plus a y. So, therefore, the first term will be a x, then you will have a y, Now this is important, you will have Ax inner product y, Ax inner product y, and then you will have Ay inner product x, isn't so? Ax inner product y, and then you have just a minute, Ax, okay. So, these are the terms Ax Ay, Ax plus y, just okay. So, not this actually. So, it will be Ax plus, so Ax Ay and then Ay Ax. Okay, maybe sorry, here I need to instead sorry x plus y, yeah, now it is fine because we have x here. So, this is the as usual Ax x, Ay y, then you will have Ax y and Ay x. Right, this is what you are going to have. Now, now let us see what it says. So, according to the assumption, this turns out to be 0, this is 0, this is 0, and here we have Axy and Ayx. But now remember this A is self adjoint. So, therefore, this Ayx is nothing but Yax, okay. This Ayx is nothing but Yax because A is self adjoint. Therefore, what you get is the following. Once you have this on this side, you get so this shows that 2 times real part of Ax y, because Yax is nothing but the conjugation of Axy inner product Axy. This is 0. So, that means this is 0. Okay. Now, if you remember that we have already seen that given 2 vectors v and w. So, this can be written as the real part of v comma w plus I times real part of v comma I w, right. This is what we know in general. So, for any x and y this holds. So, therefore, I mean if the vector space is over R, then you do not have anything to do. If it is over C, then you need to work a little bit. So, since those goes for any x and y, so this will also follow from that, right. For any x and y this holds. So, for any x and iy this will also hold, and that will imply inner product of Ax with y is 0. Okay. So, this is a proof for that. Okay. Now, we will go for unitary operators. So, as usual in the view our V is a finite dimensional inner product space over R or C. So, definition. Okay, so I think it's better to fine. Let me define that directly. So, unitary operators are nothing but the generalizations of orthogonal operators. So, therefore, A from V to V is said to be unitary. Unitary, so here we are using the term unitary as a general one. Unitary if it preserves the inner product Okay. So, you can see that if the vector space is over R, then then by unitary, the unitary map is nothing but an orthogonal one. Okay. So, let me write it as a note here. It is customary to call such an operator orthogonal if f is R. Okay. If f is R, then we will call it orthogonal. So, this terminology is just for this case, otherwise we will use the general one, that is unitary. Okay. So, what are the properties of unitary maps? So, I would say that since unitary maps are defined exactly in the way the orthogonal maps have been defined earlier. So, they preserve inner product. Then for orthogonal maps we see it has I mean an orthogonal map. For an orthogonal map there are other conditions which are also quite equivalent to that. Okay. So, let therefore prove the following. So, as I am saying, what I am saying is for orthogonal map we show some properties are equivalent. What are the properties? There is orthogonal, it preserves norm, or it sends an orthonormal basis to an orthonormal basis. So, for an orthogonal map this is what we have seen. Now, we are going to establish that for a general unitary map. So, the following are equivalent. The following are equivalent. What are the following? So, as I said, the expected one, A is unitary, then for every x, norm of x is norm of x. Then what is property 3? A star A equal to A star identity, and let me write property 4 here. So, if E1 E2 En is an orthonormal basis of V, then so what the fourth property says, similar to that of an orthogonal map, the image of any orthonormal basis will be an orthonormal basis. Is an orthonormal basis of V. Okay. So, whenever we have an orthonormal basis, its image will always be an orthonormal basis. Okay, let us try to prove this theorem. So, this part 1 to 2 is actually obvious, because so obvious actually. In fact, the same proof for orthogonal operators, the same proof goes here. For example, this part is inner product of A. If you square, I mean, in order to show these two equal, then it's enough if you show that they will be equal when they are raised to the square power, because they are non-negative quantities. So, norm of inner Ax square is Ax inner product Ax, that is same as the x inner product x, which is nothing but norm x square. Okay, so 1 to 2 is obvious. Let us talk about 2 to 3. So, in order to show 2 to 3, what one can do is Observe that given any operator A star A is self adjoint, right. Given any operator A star A is always self adjoint. So, I will make a note here, let us say for any operator A, linear operator of course, for any linear operator A from V to V, A star A may not be self adjoint, however, A star A is always self adjoint. Is self adjoint. So, we were going to use that. So, we need to prove this A star A equal to A star A is equals to identity. So, remember that we have condition 2, that is for every x in V we do have x x. Okay. So, now we use the definition of as adjoint. So, this will be same as A star A x. Now, what does that imply? If you bring everything to one side, x A star A minus x, this becomes 0 for every x. Now, A star is a self adjoint, therefore, A star A minus I is self adjoint. Now, we can easily use this lemma that we have proved over there. This implies the map A star A is identity, okay, because A star A minus I is 0. And in order to prove the other part, you have to realize that I mean to prove the other part, you just observe to prove A star equals to identity. Observe that eta star star is A. Okay. This is A. So, yeah. So, we have proved that for any operator, as long as it satisfies this, then A star A becomes identity. Now, it is easy to see that for A star the property is also obviously there. So, what I mean by that is or we can think of proving it A star A. So, what about can we say this? So, A x equals norm A x equals to, so can we say this, that given 2 implies that A is unitary, A is unitary. So, whether this holds or not, can we say that? So, A star A is here, we do have A star A is identity. So, once we have that, then A star x is equals to, for us it becomes A star x, right, A star A, then this we can realize at A double star, just a minute. So, or can we do it A star A x is this, when we try to let us see that whether we can prove this or not. well, maybe we can bypass this for the time being, and then it will imply, okay, I think the clever way is this, more clever way is this. Okay, let us see, maybe that one will work, otherwise we will go back. So, for the time being, let us remove this from the statement. For the time being, let us see, let us see that ultimately we can get this part or not, get that part that we have erased or not. So, I mean after this modification 2 implies 3, then we will try to show 3 implies 4, okay. Then we will try to show 3 implies 4. So, in order to show 3 implies 4, what we have to do is, we need to show the what happens to this. Okay. So, in order to show that this is orthonormal, in order to show this is orthonormal, we have to show that for any I j, this is the delta I j. Now, we simply use that E I A star A j, and that is exactly delta I j. So, 3 implies 4 is also obvious. Now, let us prove 4 implies 1. So, 4 implies 1 is also quite trivial. So, if you take x y in V, write x as x 1 E 1 plus x n E n. Similarly, y you write as y 1 E 1 plus y n E n, y n E n. So, you have A x is nothing but x 1 A E 1 x n A E n x n A E n, y is as usual okay. Remember, it's you have 4, that is E1 you have, therefore, now you have E1 to n is an orthonormal basis and A1 to E n, that is also an orthonormal basis. So, therefore, whenever you have orthonormal basis, then what will be the inner product of A x A y? If you just calculate it here, given an orthonormal basis. So, the inner product is easily seen to be x n y n, and that is same as this is also same, hence they are the same. Okay. So, thus what we have proved is, so these 4 conditions are equivalent. Okay. Now, if we want to get the other part, that is A star is identity, how can we get that? Let us see whether once we have this equivalence, from then whether it follows or not. Oh, then it actually it follows immediately. I am telling you why it follows immediately. That is in fact from a much more general consideration, nothing to do with orthogonal or adjoint. So, if any of these conditions hold, then the map becomes orthonormal, hence this is orthonormal. This is orthonormal. So, it shows orthonormal maps are, since this basis is going to be mapped to a basis, because orthonormal basis is a basis. So, its map is again a basis, therefore, an unitary map is automatically invertible. Is invertible once we know it is invertible and we have A star A is identity, then it immediately follows that A star is nothing but the A inverse, and therefore, automatically it follows that A star has to be identity. Yeah. So, instead of trying to, I mean what we are earlier doing, that if A preserves norm then A star preserves norm, maybe that can be shown, but actually we do not need that, it follows from more general consideration. And that also shows that for an invertible metric, for an unitary map, its inverse is just its adjoint. Okay. Fine. Okay. And as a corollary of this theorem on the properties equivalent to that of this equivalent to become unitary is this one coupled with that is it says corollary A is unitary implies A is normal. That is what I am saying, that this shows that the being unitary is same as having A star equal to identity, and then we get A star is also identity. So, A star is star A is normal. Okay. A is normal, and then we do have the spectral theorem of we do have spectral theorem for general normal operators, and that gives us the spectral theorem for unitary operators. But however, if you remember for normal operators the spectral theorem that we proved that required the vector space should be over C. Okay. So, therefore, here what we prove as a consequence of that is the following: spectral theorem for unitary operators over over C. Okay. In fact, from this point we can adopt the following convention. Before that, let us observe that this equivalence of the 4 properties that holds irrespective of f is R or C. Okay. So, this holds for orthogonal maps and this holds for general unitary maps, but yeah. So, here the word unitary has been used in a general sense, but now for the simplicity we can adopt the following generalization, the following terminology or following convention, that if the vector space is over C, then we will call it unitary, or otherwise I will call it strictly orthogonal. So, we have kind of differentiated the cases. So, this is therefore, now we simply say unitary operator, because our convention is we will use the word unitary when the vector space is over C. Okay. But do not just confuse here unitary used in the word unitary used in a general sense, that is it includes both unitary in this sense and orthogonal. Here I mean the terminology is here, as I said, that if the vector space over C, then only we will call it unitary, otherwise call it orthogonal. So, completely we differentiated 2 cases for our simplicity in referring. Okay. So, V will let V be a let V and inner product finite dimension inner product space over C inner product space over C over C then and be unitary then remember I would like to remind you that now the word unitary is reserved specifically for the vector spaces over C, otherwise call it orthogonal. So, yeah, be unitary, then there exists an orthonormal basis orthonormal eigenbasis. Okay. So, given a unitary map, that is here unitary means is a map satisfying, and there is a map on a finite dimensional vector space over C satisfying one of these equivalent properties, and then there is it has an orthonormal eigenbasis, that is you have an orthonormal basis with respect to which if you write down the matrix of A, then you will get a diagonal matrix. Okay. Fine. One more thing, even in this sense, so earlier we have seen if a map is orthogonal, then its matrix with respect to a orthonormal basis is an orthogonal matrix. So, here if it is unitary, that is over C, then its matrix corresponding matrix will be unitary. That follows from this, okay, because matrix of A star is star of the matrix of A. Okay. So, this is what we see for the spectral theorem for unitary operators, but now it makes us curious to ask regarding what happens to orthogonal operators, because both orthogonal and unitary operators are defined by the same property, and they have this properties as well, irrespective of irrespective of the bottom field, they have these properties, and then unitary operators have a spectral theorem. So, it is very natural to ask whether what happens to the orthogonal operators. So, first of all, unfortunately for orthogonal operators, you cannot have an eigenbasis. The classic example for this is the following, that you take a rotation in some direction, let us say 90° anti-clockwise. So, 0 1 minus 1 0, this does not have an eigenvector at all. So, this orthogonal map X maps to this R2 to R2, this is certainly an orthogonal map, but it does not have an eigenbasis, in fact it does not have any eigenvector at all. So, then the question is what kind of spectral theorem. So, certainly this cannot happen. So, can we have some version of spectral theorem for orthogonal operators? So, this is what we will see now. Again, let me repeat that both orthogonal and unitary operators are defined in the similar way, and in order to have these properties, it does not matter whether the bottom field is the field underlying field is R or C, but however having C, once you have C, therefore you have an eigenvector, and then that gives us the spectral orthonormal eigenbasis for an unitary operator. But unfortunately that is not the case for C and for orthogonal operators. So, it's quite natural to ask what happens to orthogonal operators. So, we see the following, that so for the rest of this lecture, because the complex case is totally done, so for the rest of this lecture we throughout assume that A is orthogonal, that is V is a vector space over C. So, so let me write V is a vector space over R, because the complex case is all completely done. V is a vector space over R, dimension V is finite, dimension V, there is a finite dimensional vector space, and A from V to V is orthogonal. Is orthogonal. Then the first observation is that A plus A star is which is nothing but A plus A inverse, because for any whether the photon field is R or C, A star becomes always A inverse. Okay. So what about this? So this is a self adjoint operator, right. Well, since we have the vector space over R, so as I say that it is customary to call self adjoint operators over a vector space spaces on vector spaces over R as this symmetric. So this is a symmetric operator. The reason for bringing this symmetric operator is that symmetric operators, they do have spectral theorem, right. They do have spectral theorem. So try to again understand that. So by a self adjoint operator we have either so for a self adjoint operator I mean if it is over R then it is symmetric, right. So for any general self adjoint operator well if it is over C, then we get its spectral theorem. From the spectral theorem for a normal operator over C, or is over R, then we proved separately that a symmetric operator has an orthonormal eigenbasis. Okay. So let us call it T, okay. Let us call it T. Now the question is what can we say further. So T is you have an orthonormal eigenbasis for T, okay. T has an there is an orthonormal eigenbasis for T. Thus V is written as the direct sum of V lambda. So what is V lambda? Lambda is, since this is diagonalizable, so it is the V will be the sum of the direct sum of the eigenspaces, is an eigenvalue of T. Yeah. Okay. And this is nothing but kernel of T minus lambda I. Okay. So as I said, we cannot have a spectral theorem like this for orthogonal operators. This is a counterexample for that. Therefore, we will try to get we will try to guess as much as we can. So therefore, we will try to somehow decompose the entire space. Of course, we will not have a diagonal matrix, but we will try to achieve a block diagonal matrix where the blocks are in a sense very well behaved and do not have big size. So we will see that. Yeah. So this is a decomposition of V into the eigenspaces of T. Okay. Now let us observe that since A is orthogonal, A star is A is identity. So A commutes with A star, A commutes with A, therefore A commutes with T. Okay. Since A commutes with T, A commutes with T minus lambda I. So earlier we have proved that for a pair of commuting linear maps, the kernel of one will always be invariant under the other one, right. Therefore, we get the following. Therefore, since A commutes with T, A commutes with T. So each V lambda is T invariant. Okay. So far so good. Now from the decomposition of V into the eigenspaces for T, we do have a decomposition of V into we do have a direct sum decomposition of V into A invariance of spaces, right. All these V lambda become A invariant. So, now the work is to find a work is to make the now the work is to bring the matrix of A on each of these V lambdas into the simplest form as much as we can. Okay. So, therefore, we will now look at this. We will now look at the restriction of A on each V lambda. Okay. Remember that V lambda is the eigenspace of T with respect to eigenvalue lambda. Therefore, for every vector belonging to V lambda, one has, okay. Now, you apply T on both sides, sorry, it will be A. If you apply A on both sides, what you will get it A square, okay, plus identity times V equal to lambda A V. So, bringing everything in the one side, A square minus lambda A plus identity times V equals to 0, this holds for every V. Therefore, for this operator T square, so let me write it over here. Therefore, T square minus lambda T plus 1 is an annihilating polynomial, of the matrix of the operator A restricted to V lambda. Okay. Fine. So, observation. So, try to understand, you have a 2 degree annihilating polynomial. So, the minimal polynomial will be the minimal polynomial of T or minimal polynomial of this operator will be a factor of that. Okay. So, what factors are possible? So, what are the possible factors of this? So, it is easy to see, the observation is if lambda is equals to plus minus 2, because what about the discriminant here? Lambda square minus 4, okay. Lambda square minus 4, yeah. So, lambda square minus 4, yeah. So, the discriminant is, so if lambda is equals to plus minus 2, then one has T, this is nothing but T. So, if lambda is 2, then this will be T minus 1, okay. Fine. Now, remember that this A being normal. So, earlier we proved that for a normal operator all the generalized eigenvalues are genuine eigenvalues. So, let us try to see what it produces us here. So, if lambda is equals to plus minus 2, if lambda equals to plus minus 2, then we have either A minus lambda I, this is 0 on V I on V lambda, or we have okay. So, in either case you see every vector, so in the first case every vector on V lambda becomes sorry here 1, yeah. So, here in the first case every vector on V lambda becomes a generalized eigenvector of A with eigenvalue 1, and in the second case every vector on V lambda becomes a generalized eigenvector of A with eigenvalue -1. Since A is normal, therefore, in the first case, so if we differentiate two cases, so in the first case, so every vector in V lambda will be an eigenvector with eigenvalue lambda. So, therefore, in this case we see A is identity on V lambda, or in the second case we see A is minus identity on V lambda. So, thus what we have seen is if the lambda, if lambda here is plus minus 2, then A acts on the V lambda as plus minus identity, okay, sorry, minus plus I think, yeah. If lambda is plus 2, yeah, if lambda is plus 2, then A will act as minus identity, that is every vector will be sent to its negative, and on the case A is plus 2, then we will see that it acts as, yeah, if A is minus, just a minute, maybe I am missing or making small mistakes anyway. So, if lambda is plus 2, then we see that it acts as then A acts as identity. If lambda is minus 2, then A acts as minus identity on V lambda. So, the lambda so in this decomposition, when lambda is plus minus 2, then we have seen how A acts on that V lambda. So, then whatever basis for that V lambda we take, either we will get an identity block or a block of minus identity. Okay. So, now we need to focus on the case where lambda not equal to plus minus 2. So, next we consider the case where lambda not equal to plus minus 2. Okay. Before that, I forgot to tell you something. What is that? Yeah. So, regarding I will just take a break from here and I will come to that fact which I forgot to mention. So, like these 4 properties that actually, yeah. So, these 4 properties, what does that imply? So, as a mere consequence of this, so I should write as a corollary that if A is unitary or orthogonal, I do not care, then every eigenvalue of A must have unit modulus that is actually quite easy to prove. Forgot this to mention. So, suppose V is an eigenvector who having eigenvalue lambda, then V comma V, okay. Okay, so AV, okay. So, lambda V. So, from the first here lambda comes out, or from the second one lambda bar comes out. So, this square VV. On the other hand, this is also, since A is orthogonal unitary, but in either case you have this is same as VV, and V is non-zero, that is it is assumed as an eigenvector, therefore, that forces lambda square is 1. So, therefore, if A is orthogonal, then it will be plus 1 or minus 1, or if A is unitary, then lambda is of the form e to the power 2 pi I t. Okay. Therefore, when you are dealing with a unitary operator, that is an operator over C, then the diagonal matrix which you get out of your diagonal matrix that you get using the spectral theorem, that has all the diagonal entries of this form. Okay. Yeah. Now let us come back to the case of orthogonal operators. So, what I have said is, for the eigenvalues, where for the eigenvalues lambda, which is either plus 2 or minus 2, for them we do have either an identity block of some size or a minus identity block. Okay. So, try to understand, therefore, in the matrix which we are the matrix of A, which we want to write using this decomposition in that matrix. So, if we first arrange V lambdas in such a way that the for lambda equal to plus 2 or minus 2, those summands will appear first, then the first few blocks will be of this form, either plus minus identity with different size perhaps. Okay. So, what I am doing is, let us say, and then we have to take care of the rest, which we will do now. So, with this decomposition, let me repeat, with this decomposition, first we arrange those V lambdas for which lambda equal to plus 1 or plus 2 or minus 2, and for those lambdas whatever orthonormal basis you take, whatever basis or orthonormal basis whatever you take, you will always get either identity or minus identity. So, now the rest is to deal with the restrictions on V lambda, where lambda is not equal to plus 2 or minus 2. Okay. How to deal with that? So, lambda, here we have lambda not equal to plus minus 2, and the minimal polynomial and the annihilating polynomial, and annihilating polynomial is this 1. So, on V lambda, so therefore, we do have A square minus lambda A plus identity equal to 0 on V lambda. All right. So, now let us see the following: choose any w in V lambda. Okay. Choose any w in V lambda. So, now we look at a w. So, we will just finish with this observation. So, a lambda, then a lambda does not lie in the span of, say, span of w. Why? Because if it lies in the span of w, then, so let us start with a non-zero vector instead. If this is mu w, then mu becomes an eigenvalue of the restriction, eigenvalue of the operator A restricted to V lambda. Okay. So, if A restricted to mu is an eigenvalue, then it must be a root of the annihilating polynomial, but we see that it cannot happen. Okay. So, therefore, this cannot happen, hence the linear span has dimension 2. Okay. So, in the I do not have much time to complete the case when lambda is not equal to plus minus 2, complete this case. So, we will complete the case in the next lecture. So, we finish this lecture with this observation that in this case, if you take any non-zero vector A, in vector w and AW, the span has dimension 2. Okay. So, I finish this lecture. Thank you.